Okay, so here are our notes. We're finally writing down some of the derivative shortcuts. So derivative formulas is our notes. And I wanted to show you the formula packet. There is this section on calculus. And notice section 6.1, this is the first principles formula that we just had our quiz on. And then if you look at 6.2, this might look a little bit familiar when you have x to an exponent. And if you take the derivative, you get the exponent times x to the exponent minus 1. Now, notice there's a whole bunch of other formulas in here. We're going to get to these. They're actually, pretty just simple. Not too much going on. The hard ones are actually down here. The chain rule, also known as Harold's First Law, version 2.0. And then next week we're going to learn the product rule and the quotient rule. So right now I'm going to put some examples into your notes using this one right here and this one right here, the chain rule. Okay, so the basic derivative of a polynomial function and the chain rule. Okay, so derivative formulas. So the first one is just for polynomials, so like x squared, x cubed, 2x squared plus 3x, stuff like that. So our basic, this is just our basic formula, which is the one that most people, when they're taking pre-calculus or calculus, it's the first one you learn. So the formula is f of x. If f of x equals x to the n, then the derivative is equal to, you bring the exponent down in front and times that by x, and you subtract 1 from the exponent. Okay, so there's the formula. So very simple. A couple of examples on that. If I have f of x is equal to x to the 5th, then f prime of x is going to be equal to the 5 comes down in front, and I minus 1 from the exponent, and voila, that's it. Okay, another example. How about if I write y equals? If I write y equals, and I have x to the 3rd, then this is going to be dy dx. And I take my exponent, multiply it in front, take my x, subtract 1 from my exponent, squared. Okay, now we can also have a coefficient of the x here. So if we do that, so let's say f of x is equal to 3x to the 4th, then the derivative, I'm going to multiply 4 with the 3, and I'm going to subtract 1 from my exponent. Okay, I can also add these together. I can have a whole bunch of these all lined up next to each other. So for example, if I have, let's see, I'll write it as y equals. If I have y equals x cubed plus 2x squared minus 4x, I can then do dy dx, my derivative, multiply the exponent in front, subtract 1 from the exponent, do it for the next term. 2, multiply it by the number in front. 2 times 2 is 4. Subtract 1 from the exponent. 2 minus 1 is 1. And then my invisible exponent here. My invisible exponent is a 1. So 1 times negative 4 is negative 4. And then I have to subtract 1 from the exponent. 1 minus 1 is 0. X to the 0 is just 1. So there's no more x's. And there's that one. Okay, so those are our basic, straightforward polynomial functions. Okay, so the ones that we're getting a little bit harder is if we had some fractions, when we had some fractions. So it's still the same basic rule, but now we're going to do a couple that have some fractions. So if I have, my example, 8x squared minus x plus 1 over x minus 3 over x squared. So you had some like this in math space. So the first thing is we want to rewrite the fractions so that they are not fractions. We want to rewrite these with negative exponents. Okay? Oh, and I should have written, sorry. Always doing stuff like this. This is my f of x. Okay, so what I first want to do is rewrite with negative exponents so that I don't have any x's in my denominators. So no x in the denominator. Okay, so I'm going to rewrite it. Still f of x. I haven't started to take the derivative yet. So 8x squared, that one's still fine, minus x. Now this one, when it's in the denominator, the invisible exponent is a 1. So when I move it, when I change its position, I have to change the sign of its exponent. So this is going to be plus x to the negative 1. Okay, and given that there's a 1 here in front, I could write the 1, but I don't need to. Okay, and then the next one, minus, I still have my 3 that's in the numerator. It's not going to move anywhere. And this one, I'm going to move it to the top, and when I do that, it's going to become x to the negative 2. So whenever you change position between the numerator and the denominator, you need to change the sign of the exponent. All right, now we're ready to take our derivative. So f prime of x. 2 times 8 is 16. 2 minus 1 is 1, so I still have my x. This one here, remember my invisible exponent is a 1. 1 times negative 1 is my invisible coefficient, so that would be negative 1. 1 minus 1 is 0, so x to the 0 is still just 1, so I don't need to write an x. Then the next one, I'm going to have negative 1, multiply it by the coefficient, which is an invisible 1. Negative 1 times 1 is negative 1. X to the, remember I got to do 1 minus 1, gives me negative 2. And then here, negative 2 times negative 3 is positive 6. And I need to subtract 1 from my exponent. Negative 2 minus 1 is negative 3. Now, for math space, they don't like the answer written with negative exponents, so we're going to rewrite it with positive exponents. The first term is still okay. The second term is fine. The third term, however, we need to move the x to the negative 2 back into the denominator. So it's going to be 1 over x squared. And then the next one, plus 6 over, notice I'm only moving the factor that has the negative exponent. So that would become x cubed. So there it is with, can you see that off the bottom? There it is rewritten with positive exponents. Okay, so then we rewrite with positive exponents. Okay, perhaps the hardest one in math space is going to be when you have something like y equals x squared plus 2 over x cubed, something like that. How do we take the derivative of this one? Okay, so we can rewrite this. Again, we're going to rewrite it without a denominator. So rewrite with negative exponents. So I'm going to want to move this to the top, but you got to be careful when you do this. You need to put the x squared plus 2 into parentheses. So it's going to be x squared plus 2, because all of this is going to get multiplied by x to the negative 3. Now I can distribute. So I'm going to have x to the negative 3 times x squared plus x to the negative 3 times 2. So I'm distributing. And then I'm going to go ahead and simplify that. when I have multiplication with the same base, I can add the exponent. So that's going to become x to the negative 1 plus, here I like to write the 2 in front, put the coefficient in front, or the constant part of the factor in front, x to the negative 3. Now I can use my rules of derivatives to find my derivatives. So this is going to be dy dx. I'm going to multiply by negative 1 in front, and then I'm going to subtract 1. So negative 1 minus 1 is negative 2. And then this one, negative 3 times 2 is negative 6. And I'm going to subtract 1 from the exponent, negative 4, and then rewrite it with positive exponents. So dy dx is equal to the negative 1 stays in the numerator. This is going to move to the denominator and become positive, minus the 6 stays in the numerator, just moving the part with the negative exponent. That becomes x to the 4th. Okay, we could actually take this one step further. We could add our fractions together. In order to add fractions, we need to have a common denominator. So this is kind of like extra step, in case you're asked to write the answer as a single fraction. Extra step. We're going to add these together. So first we need to get a common denominator. I can make x squared look like x to the 4th by multiplying it by x squared over x squared. So I'm going to take, I'll take another color. I'm going to multiply this by x squared, and this second fraction is going to stay the same. So my first fraction becomes negative x squared over x to the 4th. X squared times x squared is x to the 4th, minus 6 over x to the 4th. So dy dx, my derivative, dy dx. And now I can add my fractions together because I have a common denominator. So I add my numerators, so negative x squared minus 6, all divided by x to the 4th. Okay, so I could have done it like that. And there you have it. Okay, next, chain rule. So the chain rule, also known as Herold's first law, is when we have a situation, so chain rule, where we have a function inside of another function. So on the formula packet, what does that look like? On the formula packet, they have, okay, so this is a little confusing looking. So they have y equals g of u, and u is equal to f of x. So basically it's a composite function. So I'm going to write this slightly differently than how they have it in the formula packet. So I'll start with what they have. So they list it like this. They say if y is equal to g of u, you have some function, but that u is equal to another function, then you have a rule where you can basically take both derivatives and multiply them together. It's basically what we're doing. So I'm going to write this another way. So instead of writing like this, I could write it as, or another way of saying this is y is equal to g of f of x. Okay, one function inside of another function. All right, so how do we get the derivative of this? The derivative is we take the derivative of the first function and we multiply it by the derivative of the second function. Okay, so we take the derivative of g of x and then we multiply it by the derivative of f of x. So the way that this looks in the formula packet is it looks like this, dy dx, the derivative, here's the derivative, is equal to dy du. So that would be the derivative of this function times du dx which would be the derivative of this function. You just multiply them together. So I think it's easiest to do this with an example. These formulas I don't think are very self-explanatory, so let's do it with an example. So the examples that we did in class, we had, say, y is equal to, let me go to an example. Here we go. Y is equal to x squared minus 2x raised to the 4th power. So if I call this right here, if I call this u, we call this U substitution, then I can rewrite this as a very simple function. Okay, so U substitution, by the way, is really super useful way of dealing with complicated equations. In fact, I think I already did some notes where I used some U substitution, so I'm going to go ahead and use U substitution. So I love using U substitution. When things are complicated, make it simple. Get rid of the part that's driving you nuts. So we're going to use U substitution. So what I'm going to do is I'm going to take this part in here. This is my f of x, basically, and I'm going to change it to a u. So u is equal to x squared minus 2x. So if I rewrite this then, y is equal to u to the 4th. Okay, or I could put parentheses to the 4th. This is now my u, so u to the 4th. Now, can we take the derivative of that? Yes, that's super easy. I can take that derivative. So dy du, see, this is where the dy du comes from. Dy du, because I don't have an x, is equal to, I bring the exponent down in front, keep my variable, subtract 1 from the exponent. There's my dy du. But the formula says I now need to multiply that by du dx. So du dx is going to be the derivative of the inside part. So now we're going to find the derivative of this. So u is equal to x squared minus 2x. So I'm going to find that derivative. So that's du dx. Okay, because normally this would be a y, dy dx, but I'm using a u because that's what my u is equal to. And then there I get 2x minus 2. Okay, so now I'm going to go ahead and substitute back in what was my u. My u was x squared minus 2x. So this one I can substitute back in. Well, actually, you know what? Let's go ahead and multiply them first, okay? Because now my formula says I can just multiply these two together now. So my dy dx, the whole derivative is going to be this one times that one. So 4u cubed times 2x minus 2. And I need to substitute back in for my u. So dy dx is equal to 4 times, what was u? X squared minus 2x, and then to the 3rd. Okay, so I'm substituting back in my u. So substitute back in for u times 2x minus 2. So there is my derivative function. I'm not going to bother expanding it and simplifying it because, frankly, the reason why we use the derivative is we usually want to find when is the rate of change 0. The rate of change is 0, like at the vertex of a parabola, but also at those stationary points, maximums and minimums, global maximums and minimums, and local maximums and minimums. So we really don't need to change this into another form because I'm usually interested in when does this equal 0. So we want to actually keep it like this. Okay, so that's going to be our final answer on this one. Okay, let's do a couple more examples, and I'll do it more like how we had it in class. So slightly more simple ones. So if I had y is equal to, actually let's do an f of x one. Because here I did it with the whole U substitution and everything, but let's do a simple one where we don't need to do U substitution. So like the ones that we had in class. So if I had, for example, 4 times parentheses 2x squared minus x to the 5th power. Let's do that. Okay, so what we need to do is we need to take the derivative ignoring this. Okay, so we're going to ignore this for a second. So I'm going to bring my 5 times my 4. So I'm not going to multiply them together so you can see what I'm doing. And that's times 2x squared minus x, keep that. Subtract 1 from my exponent. But then, remember what we figured out in class, we needed to then take the derivative of what's inside the parentheses and multiply that with it. So the derivative of what's inside here, 2 times 2 is 4, so 4x, minus the invisible exponent here is 1, so bring down my 1, and then the x goes away because 1 minus 1 is 0, so I don't have any more x's left. Okay, and then we can simplify that a little bit, and we get 20 times 2x squared minus x to the 4th times 4x minus 1. And we can just leave it like that. We don't need to keep going. Okay, so there it is, doing it without U substitution. And we can even do it with fractions. So for example, if I have y equals 4 over, let's do something really crazy, the square root of 1 minus 2x. Okay, first of all, we don't like having stuff in the denominator, so we're going to rewrite. So rewrite, and we also don't like having square roots, so we're going to rewrite with fractional negative exponents. So I'm going to keep my 4, and then this, I'm going to put into parentheses, 1 minus 2x. Actually, you know what? I'm sorry. Let me back up. Let's do it one step at a time. I'm getting ahead of myself. Let's do 4 over, now the 1 minus 2x, instead of writing it with a square root, we can raise that to a fractional exponent. Square root is the same as 1/2 as an exponent. Now let's move it, okay? So I wrote the square root, I wrote it as a fraction. Now I'm going to move this whole thing to the top, and it's going to become negative. So y equals 4 times 1 minus 2x to the negative 1/2. Now, make sure you don't try and distribute that 4. I've seen people try and do this. Order of operations, exponents happens before multiplication. You cannot change this to 4 minus 8x and try and simplify your life. No, doesn't work. Cannot do that. Against the laws of the universe. Okay, so now we're going to ignore this part. We're going to take our derivative. So we're going to do negative 1/2 times 4. So my dy dx is equal to negative 1/2 times 4. Keep my parentheses. Now, the exponent, I have to subtract 1 from the exponent. Negative 1/2 minus 1 is negative 1.5, which is the same as negative 3/2. Okay? Negative 1/2 minus 1, that's the same as negative 1/2 minus 2 over 2. Negative 1 minus 2 is negative 3. And keep my denominator. Okay? This is my exponent. Okay? And now I need to multiply that by the derivative of inside the parentheses. The derivative inside the parentheses is negative 2. Okay, so don't forget this is the derivative of the parentheses. Don't forget that. That's that part. Okay, and now I can simplify it a little bit. So I have dy dx. And negative 1/2 times 4 is negative 2. And, oh, and I can times that by negative 2. Bring that to the front. And then I'm going to have 1 minus 2x to the negative 3/2. So I'm going to go ahead and change this back to a fraction. So dy dx. Negative times a negative is a positive 4. And I'm going to move this to the denominator, because see how it's negative. So this whole thing is going to go to the bottom, 1 minus 2x. And I can change that back to a positive. And then I can even change it back into a square root, because I have the square root. The denominator is 2 here. So that would be 4 over square root of 1 minus 2x. And I got to keep my cubed. Cubed. There it is. So there it is, rewritten with positive exponent and no fractional exponents. So if this was in math space would probably be fine with that, but this kind of looks a little bit cleaner using the square root rather than the fractional exponent, but they are certainly equivalent to each other. Okay, so U substitution, I showed you one example with U substitution, and you can do the U substitution and do it sort of the step-by-step way, where you find the derivative of U, find the derivative of the function, and then multiply them back together. Okay, you can do it that way, or you can just do it sort of the more shortcut way, which is multiply the 5 times the 4, keep your original part here, and then multiply by the derivative of what's inside the parentheses. Whoops, you can't see what I'm pointing at. Sorry about that. Okay, so here's doing it without the U substitution. Again, without the U substitution. Here's the example with the U substitution. I'm kind of feeling like maybe I should do one more with the U substitution, just so you get used to the idea, because U substitution is a really nice way of doing things. So let me find one more example that I could do with the U substitution. I don't have one handy. I'll have to just make one up. Okay, so let me make one more up, and I'll do U substitution. So let's say f of x. Actually, I'll make it y. It's easier, I think, to do U substitution with y equals. So instead of f of x equals, I don't know why, I just like to. All right, so another example. So if I have, let's say I have negative 5 times 3x cubed minus 2x squared plus 1 raised to the 3rd power. Okay, my u is going to be equal to what's in the parentheses. So therefore, this is now y is equal to negative 5 u to the 3rd. Okay, my u is what's inside the parentheses. So now I need to take the derivative of this, and I need to take the derivative of my u. So dy du is equal to 3 times negative 5 is negative 15. 3 minus 1 is 2. And then I take my du dx, the derivative of u. Okay, so let's bring this down here. U equals 3x cubed minus 2x squared plus 1. Take the derivative of my u. 3 times 3 is 9. X squared. 2 times 2 is 4. X, and the 1, that just goes away. Okay, because it doesn't have an x. X to the 0. 0 times 1 is 0. And now I'm going to multiply these back together. And one thing I forgot to point out before, why do we multiply? Look what happens when I multiply these together. dy du times du dx. Before I substitute these in, I just want you to notice something. Du cancels with du, and so that leaves me with dy dx. So that's why this works. That's how we can get dy dx out of this U substitution, because these guys are just going to cancel out. Okay, so let's do this now. Dy du is negative 15 u squared times du dx is the 9x squared minus 4x. But notice I have an extra variable in here, so don't forget to substitute. So this is my dy dx. Sub back in for the u. So that's the thing about U substitution. You got to remember to sub back in. sub back in for u. Okay, so we got to put the original u back in. So dy dx is equal to negative 15 times 3x cubed minus 2x squared plus 1 squared times, oh, and I should have put that in parentheses, sorry, times that whole thing, times 9x squared minus 4x. Bam. There it is. Okay, so if we had tried to, imagine if we had tried to multiply this out, expand this and multiply it out, and then take the derivative, killer. So this accomplishes the same thing. Sure, it looks like a mess, but again, we only want a function so that we can then set it equal to stuff and figure out what is the slope of the line, or sorry, the slope of the function at given points. Okay, so it's fine if it's not multiplied out. This is good enough. Okay, so that was like, what, 2 hours of notes? Sorry about that. No, it was 30 minutes. That wasn't so bad. So I'm going to set up just a couple of problems in MathSpace so you can try out the chain rule. So good luck, and if you need more examples, I think I covered everything though, negative exponents, radicals, dividing, so hopefully you have enough examples in there now. All right, have a good weekend. Bye-bye.